Hello everyone, my name is Tamim. My group name is Nexus Scholars, and me and my team are going to present a physical pendulum. First of all, what is a physical pendulum? A physical pendulum is any rigid object that swings back and forth at a fixed pivot point under the influence of gravity. Unlike a simple pendulum, which assumes mass at a single point, a physical pendulum accounts for objects' whole mass distribution and rotational motion. Set up a physical pendulum. First, we need a rigid object. This is a rigid object. Second, we need to suspend it from a fixed point so it can swing freely like this. Now we have to measure the whole scale from the pivot point, which is L. In our case, L is 31.9 centimeter.
For the experiment, we displace the pendulum slightly, less than 40 feet to maintain the simple harmonic motion. Release it gently and let it oscillate freely. We're going to use a stopwatch to record the time for 10 complete oscillations. To calculate the average time period, we're going to divide the total time for 10 oscillations by 10, which is 8.71 by 10, and then we got 0.871 second.
For a uniform rod, the moment of inertia is I equal to 1/3 ml square. M equal to mass of the pendulum, L equal to length of the scale from pivot point.
The formula for the time period T equal to 2 pi root over I by mg is, while is I equal to moment of inertia, M equal to mass of pendulum, G equal to gravity, H equal to distance between pivot to the center of mass, T equal to time period.
To calculate the time period, we know T equals to 2 pi root over I by mgh, where we know I equals to 1/3 ml square. And we know h equals to L by 2. After some calculation, we get T equals to 2 pi root over 2L by 3G. We're going to put L and G's value into the formula. So we get T theory equals to 0.92 seconds. To calculate the error rate, we get measured time period 0.871 second and theoretical time period 0.925 second. To calculate the error rate, this is the formula. After putting the value, we get 12.9%, which is our error rate.
Causes of the error: friction at the pivot reduces oscillation amplitude, affecting the time measurement. Air resistance slightly slows down motion. Measurement inaccuracies. Reaction time errors when using a stopwatch. Precise center of mass measurement. Affects theoretical calculation. Angle assumption. Larger angles invalidate the simple harmonic motion approximation.